Friends, we will discuss the 22nd lecture on online course on risk and reliability of offshore structures. We are discussing lectures on module 2, where we are focusing on structural reliability. Today will be the 22nd lecture, which will talk about variables in reliability analysis. We already said the variables in reliability analysis. Generally, if you want to talk about structural reliability, one can use Boolean variables, which we expressed in the last lecture. We said if the system contains elements in parallel or elements in series, if the elements are purely ductile, then how one can estimate the probability of failure for a given system using Boolean variables. We also said in the last lecture the variables can be represented in 4 different forms: succinct variable or succinct estimate, fuzzy number, characteristic value, and overall a random variable. In a given interval, it is important to know what is the degree of probability associated with each variable. With each variable. So, it is very important that we must know the probability of occurrence of those variables or probability of fitness of these variables in a chosen interval, that is very important. Okay. For instance, let us say for example, if V ranges between, let us say, V min and V max. One should be able to calculate, or one should know the probability associated within this interval for each variable. Of course, there can be many variables in a given system. Yesterday we saw different kinds of loads, different material strength and degradation. There can be many variables in a given system which can affect Q, which can affect R as well. Okay. So, therefore, depending on the approach to define safety, one typically uses characteristic values. So, to avoid this confusion or to get rid of this problem, one actually uses characteristic values. Characteristic values of the variables. Characteristic values are those which says will have no probability of exceedance beyond 5% of the chosen value. For example, if I say the load combination or the load or the stress value is going to be 0.95 sigma y, and I say there is no probability of exceeding this value beyond 5% during the service life of the structure. So, characteristic values have a very classical definition based on probabilistic angle. So, depending upon the approach to define safety, one generally uses characteristic value obtained by increasing or decreasing a typical value. In more appropriate terms, it is better to represent this variable by a known distribution with a density function, which is preferably. So, it is always better to express or to represent the variables by a known distribution whose probability density function can be, let us say, f v of v. But we all know that the variable has got randomness in nature. Therefore, to include the random nature of the variable, which is denoted by let us say v of omega, where omega is element of sigma, is an even space. It is important that the reliability approach what we follow should be compatible with available information. Because the randomness of the variable is a subset of a space of elements, and the approach what we follow should be able to be compatible with this space of event. So, therefore, people have chosen to use stochastic model. So, it is better to use a stochastic model to represent the random variable. Because they will be able to include the representative variability with an appropriate probability density function. Okay. Stochastic models can include the representative variations with the help of appropriate probability density function. There are two main approaches to handle this whole problem. One is what is called naturalist's approach. Other is what is called physicist's approach. Physicist's approach. The naturalist approach relies on observation of the sample, which estimates the mean, standard deviation, and other statistical moments. Statistical methods offer estimates of the random variable, and they are based on best adjustment of an appropriate probability density function which is determined and used for representing the whole model. Therefore, the chosen probability distribution function should be verified with the goodness of fit test. Therefore, you choose an appropriate probability density function and examine this function with goodness of fit test. Chi-square test, etc. Whereas, alternatively, the physics approach relies on understanding the variability of the material behavior or focus on material behavior on a macroscopic scale It includes the material behavior and characteristics under the given state of condition. Let us say for example, a Weibul's model. This can be used to identify the probability density function. Which should include the mechanism of failure of the material, which should rather include more precisely the internal defects of the random variables. Interestingly, most of the geometric based and material based uncertainties can be included in the model, but the result of reliability calculations exclusively depend on the quality of the data, which is generally insufficient. So, the reliability analysis based on both the approaches essentially depend on quality of data. Unfortunately, this is generally insufficient. It may be mainly due to the size of the test samples. The main reason for this particular insufficiency is due to the sample size or the ensemble list what you have. Bigger the number of tests or larger the sample, greater the changes of stumbling point on an unsatisfactory test. Of course, this paradox can be resolved using a probabilistic approach, which of course shows a better accuracy of the information. For instance, let us take Gaussian distribution. Gaussian distribution is one of the most commonly used probability density function. Which can represent the random variable. The difficulty with this is it represents an infinite domain. Now, this is a major defect. An infinite domain is not acceptable for reliability analysis. However, if truncations are made, then Gaussian distribution is certainly a very well adapted distribution. Okay. So, if truncations are made, then Gaussian distribution is well adapted distribution, which can give you satisfactory results because it represents central tendency is satisfactory. A typical Gaussian density plot looks like this. The bell mouth curve. This distribution suits very well with both experimental and analytical observations. That is what people have commented in the literature. It is one of the powerful density function which can accommodate both experimental and analytical observation. It is therefore interesting to note that for rare events, reliability calculation concerns the distribution tails. So, an important statement: for rare events, reliability estimates are highly dependent on the distribution tails. Look at this curve. One is interested to focus the event of probability of exceedance or probability of exceedance from the lower value. So, of course, if you look at the central tendency, this plot represents decently the distribution of the data of the ensemble, whether it is experimental or analytical. The problem comes when you use this probability density function for reliability analysis, where the events are very highly rare. When the rare events are modeled using this as a limit state function, considering the random variables are Gaussian distributed, then the reliability analysis will essentially depend on the tail of the distribution, for which the information is evidently very rare. Okay. That is why when you do reliability analysis for rare events, you can always land up in erratic results. So, what to do in such cases? In such cases, approach using extreme value statistics is better. So, in such situation, one can use extreme value statistics. This can provide a preliminary response of the physical model. Now, interestingly, it is possible to compare different assumptions to search for a better envelope in such cases. Let us say, considering a typical function which is v of x, t and omega on space, the time and random set becomes element of omega becomes element of sigma. Therefore, while fixing the random set, one can say v of x t omega naught is equal to the outcome of the trajectory of this function for a fixed element of random set. Okay. So, therefore, in such situations a stochastic process, which is also a random process, denotes such a function. So, a stochastic process which is also a random process denotes such functions with random set of variables. Okay. That is why under the given complexities of rare events, reliability analysis generally tend to become accurate when you use a stochastic process. But there is one important catch here. The stochastic process can be indexed either by time or by space. That is very important. But in this case, the general complexity is it has got both the variables in a subset. Okay. So, the stochastic process, which is also a random process, denotes such a function which can accommodate the variable only in time or in space. To understand this, let us take a quick example. Let us consider p ground acceleration of an earthquake signal. This has a spatial distribution of an elastic modulus in such cases one should perform discretization because it was a spatial distribution. So, discretizing this we can say V of x t omega can be taken as V of t omega. The spatial distribution is now compromised as V1 where x equals x1 and of course, the variables are t and omega, V2 where x equals x2 and of course, the variables are still t and omega and so on. Let us say Vn where x equals xn t omega. So, one of the distribution in terms of spatial distribution is compromised in this format to use it in the stochastic process. And the cross correlation function can be said as and so on, which can be extended as which tells me all along this is going to be a unit value. This band will be unity. Therefore, when a spatial distribution function or a variable is discretized in the form as just now we discussed, this will quickly result in large vectors. Okay. Now, what is the disadvantage of this? They become complex, mathematically difficult to handle, then what to do? One can use statistical tools. To handle such complexity. If you think that one can use software for solving such problems, please remind friends, softwares also have limitation in handling such problems. Even software has limitations in handling such problems. Then what is an alternative? Alternatively, it is a common practice to rely on stochastic model. which is indexed by time. However, in many situations it is possible to use an extreme value distribution to express the maximum and minimum within a given interval of time. For example, probability of maximum wind speed in a year not exceeding the limiting quantity can be expressed as follows. Let us say f v of v stands for the wind velocity or speed, is probability of capital V less than or equal to V, equation 1. In the n successive years, it is possible to consider annual probabilities. Which can be independent. Of course, one can use the same distribution function so therefore, one can model the maximum speed for n years as probability of V1 less than V, probability of V2 less than V is as good as function of yn probability of V, where n is n successive years, where I want to consider the probability of exceedance of this wind speed for n consecutive years or n successive years, so that that event should not exceed the maximum probable value. Okay. So, therefore, study of extreme values, that is n tending to infinity, has led to what we call extreme value distribution. Some examples of extreme value distributions can be, if you really wanted to know that a condition where n tends to infinity, then this will lead to extreme value distributions. Some of them are Gumbel, Freshat and Weibull. It is therefore possible, friends, to represent a repeated function of time by a random variable, which is one of the most important steps in reliability analysis. Now, how to handle this in mechanical modeling? Now, I want to actually model the event mechanically. So, can I handle this in mechanical modeling? The purpose of modeling is to construct explanatory and predictive model of a physical phenomena. The purpose of a mechanical model is to construct explanatory and predictive model of that of the physical phenomena. But when you attempt to do so, there will always be a decent difference between the behavior of the mechanical model with that of the physical model or physical reality. This modeling deviation is of course very normal and acceptable, provided the deviations or differences in observations are within the limits as governed by the designer or the modeler or the researcher. Procedures for validation are of course available. So, one can always validate the mechanical model with that of the physical model by comparing certain threshold values which are very important for observation in the specific behavior of the model. It can be easily seen that not a totally random behavior is seen, but contains a systematic bias. So, interestingly, if a mechanical model constructed is appropriate and govern all the modeling laws which can truly represent the physical phenomena of the specific behavior, one can see that even though there are variations between the behaviors of that of the mechanical and physical models, they will not be random totally, but they will contain some systematic bias. On the other hand, gross errors must generally be prevented while comparing this. That is what we call as quality assurance in the mechanical model when compared to express the behavior of that of a physical model. So, one can always approximate the representation of a physical reality using this curve. So, one can always approximate the physical reality using specific steps involved. Please pay attention to the chart shown on the screen now. For example, if you have uncertain data which have 2-3 digits, if you have a numerical algorithm or imprecise analog model, if you want to explain the behavior of these in terms of predictive model, then one can either go for physical reality or image of the reality. In both the cases, one should ensure that there is a low deviation between the reality and the image. If you see any gross deviation, then one can say that the quality assurance or quality control in the mechanical model is not proper. So, the mechanical model should always give, whatever may be the case, uncertainty in the data in terms of 3 digits, uncertainty in the algorithm, whatever may be the case, it should give me a low deviation as far as possible between the physical reality and the image of the reality, what we call, which should appear in the mechanical model. So, friends, in this lecture we have interestingly seen the factors which dominantly lead reliability analysis towards stochastic modeling, how the variables of multiple in nature can be handled with a little bit of compromise either in space or in time in stochastic models. We have understood the necessity and importance of stochastic modeling in reliability analysis because the classical distributions do not give information on rare events, especially on the tail ends of the distribution curves. So, reliability analysis, if done with these conventional distribution PDFs, may give you error because the sensitivity of the rare data is not sufficient in terms of the distribution properties when you use the standard probability density functions. So, one can go for stochastic modeling. So, stochastic modeling should be able to represent the physical behavior as close as in case of mechanical modeling. So, one should try to limit the difference in behavior between these two models as far as possible. We will also see in the next lecture what are those complexities which arise from mechanical modeling, how certain things cannot be completely and truly mechanically modeled which represents the physical behavior, what are those constraints. We will show an example problem how we have solved this problem using experimental studies. We will talk about this in the next coming lectures. Thank you very much.